Welcome to the Deep Dive. We take the information you're curious about, your articles, your research, and we really dig in to find the key insights.
Yep, kind of like an express route to getting the core ideas, maybe with some interesting bits you didn't expect.
Exactly. And today, we're jumping into something from algebra that might sound familiar. The remainder and factor theorems.
That's right. We've got some material here from studiestoday.com, listener provided, focusing on these theorems, our mission to understand them, how they work, and importantly, why they're actually really useful shortcuts when you're dealing with polynomials.
Shortcuts in algebra. Okay, I'm listening. I definitely remember, wrestling with polynomial long division back in the day and just thinking, ugh, there has to be a quicker way.
Right. It can be pretty tedious.
So the idea of these theorems can help skip that. That definitely caught my eye. Okay, let's get into it. The source starts with the remainder theorem. But first, it kind of sets the stage with the basic idea of a function.
Mm-hmm. The foundation.
Like it gives 5x equals 2 by 2, 5 by 7 is 7. It just shows, plug in a number for x, get a result. Put in 3, you get -4. Put in Heine's 3, you get 26.
Simple input, output.
Yeah, same deal with phi y equals 2y3, 3y plus 4. Put in 5, get 236. Put in -2, get -9. Pretty standard function stuff. Change the input, change the output.
And that's crucial. Understanding that a function gives a specific output for a specific input is key for grasping what the remainder theorem is telling us. It connects that output value to something else, something you might not expect.
Right, the remainder from division. Okay, so the source walks us through dividing, say, 5 of x equals by 2 5x plus 8 by 6 to 8a.
Yeah.
You do the lone division.
The whole process, yeah.
And you end up with a remainder of 2.
Mm-hmm.
Okay, but then it says, what happens if you just calculate 5 times? So 2 to 5 times 2 plus 80a, that's $4.10 plus 8a, which is 2.
Boom, same number.
Exactly.
Yeah.
The remainder from the division is the same as the value of the function at that point. It's like a hidden connection.
It is the connection. And it's not just a one-off. The source gives another example to really drive it home. 5x equals 6 by 3 by 2 plus 8 by 5 divided by 6x plus $3.
Okay, a bit more complex.
Yeah, the division takes longer, but the remainder works out to be -218. Now, what's 5 Bebelsers?
Let's see, 6333 plus 8355, that's $6, 27, 39, 24, 5 L. So -162, minus 27, minus 24, minus 5.
-218.
-218 it is. Matches the remainder perfectly.
Wow. Okay, so this isn't a coincidence. This is the pattern.
This is the remainder theorem. Formally, like the source says, if a polynomial values is divided by a linear expression like 60, the remainder you get is just 5x.
That's the shortcut. Instead of doing all that division, just plug the a value into the function. That's brilliant. But
Right.
why? Why does plugging in a give you the remainder?
Great question. It comes down to how division works. Remember, when you divide fixed e by xea, you always get a quotient, let's call it q, and a remainder, 5 sucks. So you can write 5x aqx plus 2x.
Right, the basic division statement. Dividend equals divisor times quotient plus remainder. Exactly. Now, the key thing is that the remainder's degree has to be less than the divisor's degree. Since sec say a has degree 1.
The remainder has to be degree 0, just a constant number.
Precisely. So we can just call it 3r. Our equation becomes favx xaqx plus $. Now, what happens if we plug in sec say ELA into this equation?
You get few a, aeqa plus r. The auxiliary term becomes 0.
Right, so phi aa plus r day, which just simplifies to...
It's a. The value of the function at a is the remainder. That's actually really elegant.
Isn't it? It flows directly from the definition of division.
Okay. So let's see in action. The source has an example. Find the remainder when 6 by 8x plus 3 is divided by $2 plus $1.
Right. So step 1, find the value of x that makes the divisor 0.
$2 plus 1 plus 1, so 6x plus $1.
Step 2, plug that value into the polynomial 5x.
Okay, so $4 plus $4, that's free $1 plus 6 all plus another 4. So $8 Shosharana.
And that's your remainder.
Yeah.
$8 Shosharana, no long division needed.
Much faster.
Yep.
I like it.
It's incredibly useful, and you can use it to solve for unknowns in polynomials, too.
Ah, like those find the value of k problems.
Exactly. Say x by $3 plus 9 by 2 plus 4 by $10 divided by $6 plus 3 leaves a remainder of 5. What's a?
Okay, the divisor is 6 plus 3, so we use other is equal 3 to 3.
Yeah.
The theorem says hope 3 tells must equal the remainder, which is 5.
Right, so plug in
3 thirds plus 9, 3, 2 plus 4, 3, 10 to equal 5, 9, 12, 10 plus 81. So 27a plus 81, 12, 10 equals 5, 1.
Simplify that. $81, 12, $10 is $509. So $10 and $7, $59 plus $59 is 5.
Subtract 59 ton $27 and dollars and is 5 $2. Divide by negative 5 $5. Divide by an x to 7 2.
See? Straightforward application. The source has a few more like this.
Yeah. Finding k if 2 by 3 k by 2 plus 5k3 plus 5k3 by 8 divided by 6 of 2 gives a remainder 14.
Combine the k terms. 6k is going to combine the constants. $16 plus 5k2 is 2, so 6k plus 2 plus $14.
So 6k plus 2 plus 12 so to get $2.
And it works even if you have two polynomials leaving the same remainder.
Oh, right. Like 3 by 3 8 by 2 tolls plus 5 by 13 3 in total and plus 1 by 2 7x plus 5 both divided by 6 by 3 tolls.
If they have the same remainder when divided by 63 tolls, then their values must be equal in $6.
So you said phi dollars the first polynomial equal to g $3 the second one.
Exactly. Plug in 3 for x in both and set them equal.
Okay. $3 at 332 plus 5332 it should equal a plus 13273 plus 55.
Which is 819a plus 1513 equals a plus 1921 plus 55.
So 839a plus 9a plus 921 plus 55. 839a equals 9a77.
Now solve for a. Add 9a to both sides, add 7 to both sides.
$90, $80. So $8 daily dollars. It works out neatly.
It does. And it gets even more powerful when you have multiple unknowns and multiple conditions.
Like finding A and B.
Yes. Example, 5x, f is 3 plus x or 2, b by 8 day. Remainder is 0 when divided by 6 tied with 2, and remainder is negative 30 when divided by 6 to $.
Okay, two conditions, two unknowns. Remainder is 0 for 6, $2 means $8, where remainder negative 30 for 6 plus dollars means 1 is to $.
Perfect. Set up the equations.
Big 2 plus A to 2B2, 8, that's $8 plus 4A, 2B, $8, so 4, 2B dollars, so 1 plus BL, so y equals 2U. Okay, now 5, 1, negative 1, 3, plus A1, 2B, negative 1, 8, plus B8 plus B8 equals 30, so 1 plus 2B9, so A plus B9, negative 30.
1 plus b equals 2 Nash and 2 under 1, 1.
Now we substitute do nars into that second equation.
Yeah.
Plus 2a equals 2120.
Yeah.
So $3 equals 2 Nash into 1.
Which gives O Nash and S $7.
And since $1, then bod equals 2 negative 7 and equals 41 equals 2.
Found both.
See how the remainder theorem provides the equations you need to solve the system?
Yeah, it's very efficient. And the last example here is kind of clever, finding what number to add to a polynomial to get a certain remainder.
Right. Add what to 2 by 3, 3 by 2 plus x's, so that divided by 6, 2 gives a remainder of 3.
Let the number be k. So the new polynomial is gx equals 2 by 3 by 2 plus x plus k day. We want g to be 3.
So calculate g dx, 2 plus 2 plus k plus 3. That's $16 plus k equals $3 plus k equals 3 twice.
So k must be
2k over 3. You need to add minus 3 or subtract 3.
Exactly. So the remainder theorem is quite versatile. It finds remainders, solves for unknowns, helps adjust polynomials, all without the grind of long division. Okay, I'm sold on the remainder theorem. Now, you mentioned its close relative, the factor theorem.
Yes, the factor theorem. And as the source material points out, it flows directly from the remainder theorem. It's really just a special case.
A special case. How so?
Well, think back. The remainder theorem says the remainder, when dividing 5x's by xa, is aa say. Now, what does it mean if xa is a factor of x?
It means it divides in perfectly.
Right.
With no remainder left over.
Exactly. No remainder, or in mathematical terms, the remainder is 0.
Ah. So if xe is a factor, the remainder of it must be 0.
Precisely, and that's the factor theorem. If x is its factor, then xa is a factor of phi x.
Okay, that makes total sense. Finding a value a that makes the polynomial 0 a root tells you immediately that xa is a factor.
Yep. The source gives 5x by 2 5x plus 6ab. Let's test 3, 2, 5 is 3, plus 6 by 6 plus 9, 15 plus 6 is a factor.
Since fix 3, the factor theorem tells us 6 by $3 must be a factor.
Which we know is true because 6 by 2 5x plus 6x factors into 6 by 3 by 2.
And the flip side works too. The source checks if the source is a factor of 6 by 5 plus by 4 plus by 3 by 2x plus 1 dot. Okay, so we calculate Funkel dollars. $16 is 15 plus 14 plus 13, 12, 1 plus $1. That's $1 plus 1 plus 1, 1 plus 1.
Which adds up to, right.
$1 is equal to, since it's not 0.
$4 is not a factor. Simple check, no division needed.
Just like the remainder theorem, we can use this to find unknowns. Like if 6 by dollars is a factor of 6 plus 2a.
If the $, is a factor, then $52 must be
0. So 2 says $7 plus 2a equals $1.
$4, 14 plus 2a equals close to
$2 does 2a else 2.
$2 is $10, a 5 seki, easy.
And it scales up. What if 6 basine is a factor of 6 by dollars plus 2a to 2kx plus $10 plus in? First, find k.
Okay, $15 must be the powers, $23 plus 2k2 plus 10 plus 10.
$2 plus 2k plus $10 little, so $8 plus $8 plus 8, 2k plus $10.
So no dollars plus 8, 2 pesos, $13, 7, $10.
So we need to check $5 for the polynomial 6 by dollars plus 2 by 2, 13x plus 10.
Let's plug it in. 5, 3 plus 2, 5, 2, 13 to 5 plus 10.
Okay, 5. There 3 is a national 25 plus $2 to 5, $2, 2 times 125, 5, 12, $125 plus 65 and plus 10.
So national $25 plus 50 plus 65 plus $10. What's that sum?
$50 plus 65, $115 plus 10 is $125. So $125 plus 125 is
Yes.
0.
So yeah, 6 plus 4 is also a factor.
C. And again, for multiple unknowns, if 6 plus 2 would be $3 are factors of $63 plus x plus b.
Factors means two roots. One are 2 and dollars, one of 23.
Set up the equations. Fun is 2 plus 8 and is 2 plus implies 9 is 8, 2a plus b plus b.
So 3 plus a3 plus b equals 0 implies 27 plus 3a plus b equals 2.
Two equations, two unknowns again. From the first, $5 is 8 plus 2a. Substitute into the second, $27 plus 3a plus 2a plus 2a.
$35 plus 5a.
So $5 plus $2 and under is 76.
And by dollars 8 plus 2a was 8 plus 2. That's how the outer plus $2.
Divided 6/7. Got it both.
And you can even mix the theorems. The source has one, 6 by dollars a by 2 dollars plus b x 66. It leaves remainder and minus 8 when divided by 6 is dollars and 622 is a factor. Find a and b.
Okay, remainder and minus 8 for $6 means 5 is $8. That's the remainder theorem.
$13 a, $1 plus b1. 6 equals then it's $8. So $1 a plus b6 equals $8 plus b5 plus b5 plus b2 plus b an equation.
And $6 is a factor means $5 is a factor theorem.
To have two colors, a2 plus b2, 6 up leaves 3.
$8 for a plus 2b6 equals it all.
$2 for a plus 2b equals $, or $1 2a plus b equals e. That's equation 2. Maybe rearrange EQ1 as ball equals to 3f3.
Sub that into EQ2. $1 2a plus a 3 equals the 3.
$1 2a plus a 3 plus a 3 because a 3 equals $5.
And ball L is a 3 equals b equals 553.
Yeah.
That's clever, using both.
But perhaps the most direct use of the factor theorem is for actually factorizing polynomials completely.
Right, breaking them down into simpler pieces. How does that work?
Well, if you can find a value a such that $5 in xa is a factor, then you can divide the original polynomial by sexa using polynomial division.
Ah, okay. So we still might need some division.
Sometimes, yes. But finding the first factor using the theorem makes the division much simpler because you know the remainder will be 0. The result of the division will be a polynomial of lower degree, which might be easier to factor further.
Okay, example. Factorize 3 by 2, 3 by 2, 2.
Let's test a simple value. Maybe 3 by $5 2, 52 2, 52 3, 3 4, 10 2 equals 12, 10 2 is a factor.
Now divide 3 by 2 times and 5 by 2 times 5 by 2. You can use long division or synthetic division. Doing the division, you get $3 plus 11.
Exactly. So 3 by 2x, 5 by 2, x equals by 2, 3x plus $1, fully factored.
Nice. And for a cubic, like 2 by $3 plus 5 by 2, 11 by $14. The source is check 2x plus $7.
Okay, if $2 plus $7 is a factor, we need to check the root 6 that $14. If I have $5, this looks messy. $2 plus $7, $14. It apparently works out to 0 according to the source.
Let's trust the source on that calculation for now. Since $5, 2x plus $7 is a factor, now divide the cubic by 2x plus $7.
Okay, dividing 2 by $3 plus 5 by 2, 11 by $14 by 2x plus $7. $6 by $2.
And can we factor $6 by 2 too?
Yeah, that's 6 by 2, x plus $1.
So the complete factorization is $2 is plus 7 by 2.
Okay.
X plus $1.
Got it. So find one factor using the theorem, divide, then factor the rest. What if you don't know where to start looking for a root?
Good point. For polynomials with integer coefficients, the rational root theorem, which we aren't diving into today, but it's related, helps narrow down potential rational roots. But often you can just try simple integer values like $1, 1, 2 at x at 2. Like for 2 by $3 plus by 2, 2 by $, is straight $30.
So it's 303 plus 1, 2, 1 is 3 plus 1, 22 and 1 third 2.
Hey, lucky first try. So 2, 3 is a factor.
Now divide 2 by $3 plus by 2 by 1 by $2.
The result is 2 by $2 plus 3x plus 1 more.
And can we factor that quadratic 2 by $2 plus 3x plus 1 other?
Right. Yes, that looks like 2x plus 1, x plus 1.
Perfect. So the full factorization is x plus 1, 2x plus $1.
Okay, this process makes sense. Find a root, get a factor, divide, factor the result.
And it works even when finding coefficients first, like finding a and b. So 6 plus 5 are factors of $60 plus x2 plus bs $45.
We did a similar setup before. F1 and $5. The source says this leads to A $3 and B $3. Wait, let me recheck the example. A $3, B $3.31 is not in the outline, but the process is key. Let's assume we found the correct A and B for this example. $6 plus X2 plus B is $45. We know there's $2 and plus $5 are factors.
So their product, 6 by 1, x plus 5, but 2 plus 4 by $5, must also divide the cubic.
We can divide $6 by plus X2 plus B by 4 by 5 with the found A and B by $6 plus 4 by 5 by 5.
Yes. Or, since we know two linear factors, the third factor must also be linear, say 6 plus c, then 6 by 1, x plus 5, x plus c by 3 plus x of 2 plus bx is x 45 priority. Expand the left and match coefficients, particularly the constant term. Well, null and 5c. We understand 45, 5. So 5c is division of 4.11, which means 2 yields $9.
So the third factor is 6 plus $9. That's neat. The full factorization is 6 by 1, x plus 5, x plus $9.
One last one. Find p if 10 series is a factor of 2 by 3 by 2 p plus 2, 2, then factorize.
Factor means 41ls 2p2, 2p2 equals
3tp2 divided by few dollars.
62 by 2p equals a fact plus.
$2. So the polynomial is 2 by 2 plus 3x plus 101.
We know 2x is $2 divided by 16.
Student adult is 2 by $2 plus 3x plus $1.
So the complete factorization is 6 plus 1, 2x plus $1.
So wrapping it up, these two theorems are really quite linked. The remainder theorem gives that fantastic shortcut for finding remainders.
Factorize the remainder when dividing by 6.
The factor theorem is the special case. If that remainder happens to be 0, then xa must be a factor.
It definitely makes tackling polynomials feel less intimidating. More about clever checks than brute force division sometimes.
Absolutely. They highlight the underlying structure and relationships within polynomial algebra. They're efficient, powerful tools.
So reflecting on this, these theorems are essentially elegant ways to get information about polynomial division and factors without doing all the laborious work. It makes you think.
Yes.
What makes you, the listener, think? Where else do these kinds of insightful shortcuts appear? Maybe not just in math, but in other problem-solving situations. Are there times when understanding a core principle or relationship lets you bypass a much more complicated step-by-step procedure?
That's a really interesting question to ponder. How understanding the why behind something can sometimes unlock a much faster how. These theorems are a great mathematical example of that.
Definitely something to think about.
Yeah.
We hope this deep dive has helped clarify these theorems and maybe even spark some new connections for you. Thanks for joining us.